Good afternoon, everyone. This is lecture number 10, E524, Digital MOS LSI Circuits. Today is September 29, 2020. So we have studied CMOS inverter, in which we know that this is a CMOS inverter. This is VDD and ground, and this is input output. We also learn some of the specifications required to design such a CMOS inverter. Those specifications are switching threshold, we also learn about noise margin, we also learn about propagation delay. On top of that, you need to find out the power consumption, which we have not studied, but yeah, this is one of the listed specification for an inverter. Moreover, we also learn that the drain current, when it's in like whichever region my transistor is, for NMOS transistor, this is equal to VGS minus VTH times VDS minus VDS square by 2. Some people also write like this, Kn times VDS times VGS minus VTH minus VDS by 2. Notably, when the transistor is in saturation, we are adding one extra word, which is known as VDS sat. This indicates that it's in saturation mode of operation. As we know that there are various modes of operation. One of them is cutoff. Another one is linear or triode. And another one is saturation mode of operation. I'm keeping this because of some reason, because I was talking to Nandit and I realized that he got some of the confusion over here. So there is a sentence over here where the analog designer would bias the amplifier in the middle of the transient region so that the maximum linearity. So analog achieves the maximum linearity and the digital is achieving the extreme non-linearity. So his question was, look, our CMOS inverter is the one which is operated in the linear mode of operation. Let's come back to where we were, but his question is, like, if we are using the digital where it's extreme non-linear, and analog is actually extreme linear, what does it mean actually? So the book wants to say something else than what you are understanding. If you have doubt on this, what exactly it wants to say that digital is the one which is dealing with the large signal, and analog is the one which is dealing with the small signal. Now let's assume that we are talking about the analog and there is an amplifier whose gain is around, let's say, 10 and whose supply voltage is VDD and let's say minus and plus VDD, which is plus 1 and minus 1. Now let's assume that if I am applying here the input as something like 0.01 volt of sine wave, so up and down 0.01. So at the output, I can see that the output will be going from zero point 0.1 to minus 0.1, no problem. If I am applying here 0.1 volt plus or minus, I am going to see this one as 1 and minus 1. So still there is no problem. Look, when you multiply V in with respect to the gain given in this triangle, you are going to have the V out. It's a linear relation, right? So the relation is really linear as long as it's a small signal input. Means if you are going beyond this 0.1 volt, because it's the dynamics of this amplifier that the gain is multiplied by 10. If it is multiplied by 100, then this will not be the small signal input. But in the case of multiply by 10, if you are giving 1 and minus 1 as input, let's assume that this is 1 volt and minus 1 volt. If I am giving, the output will not be look like this one, but it will be look like this one. Actually, this wanted to go to plus 10 and minus 10. However, it cannot go there because of the reason that the supply voltage is plus 1 and minus 1. So it will be saturated and it's as good as it's a square wave, or you can say that such kind of non-linearity is actually known as the saturation. If I draw V in with respect to V out, which looks like this one, so as long as you are in this particular region, you are in small signal, this is small signal, whereas if you go beyond that, it's a large signal or it's a saturated one. So here when you are using the digital circuit, which is the large signal, it's actually an extreme non-linearity whose name is saturation. Whereas this analog circuit is the one which is inside the small signal regime, where output does not get saturated to VDD and ground. Hence there is no saturation. So that's a extreme linear and other side is extreme non-linear. So that is the meaning of that particular sentence. Okay. So let's come back to what we were talking about. So this is the current equation, and you might be interested in writing out for PMOS, then it will become KP and all such things will be there, where VSG will be replaced with mod of VSG, and VTH might be same or might be different also. In most of the cases, the threshold voltage of NMOS and threshold voltage of PMOS are not equal to each other. They are different and it's a technology dependent, which needs to be taken into account. Okay. Other than that, Kp is or Kn are the constant which are mu Cox times W by L. So this is mobility, this is oxide capacitance, width and length. All these things are depending, and first part we are calling it Kp prime or Kn prime, depending on what subscript you are using over here. And accordingly, you can write down the things. So all these things we have studied and we become expert on that. And we also learn that noise margin high, okay, before noise margin high and low, the voltage transfer characteristic look like this one. Notably, this is a DC characteristic, and this is known as the voltage transfer characteristic, where you are changing the voltage from 0 to VDD. You are saying the output from VDD to 0. There are various things we have defined. This point where the slope is changed and it's -1. Another place where again slope is -1. these 2 points are defined as VIL and VIH. Other side, this is going to be defined as VOH, and this will be VOL. So from here, you can find out that noise margin high and noise margin low are equal to, so noise margin high is VDD minus VIH, and this one is VIL. From here, you can find out the required things. So this is noise margin. Other than that, we also learned that switching threshold voltage, which is the midpoint when the transition is going from 1 to 0 or 0 to 1, that is going to be the switching threshold. So we generally desire to have Vin equal to Vout equal to VD by 2, that's equal to VM. By the way, VM is the one which we are calling it switching threshold. So all these things we studied, and on top of that, we also studied that the propagation delay. Which say that we are going to follow the Elmore delay, and in Elmore delay, we are keeping 0.69 times path resistance times the capacitance looking at that particular node. So this is the Elmore delay. We are measuring at 50%, that's why it's 0.69. However, if you are interested in finding out the rise time and fall time, we are going to measure it at 90%. And for 90%, you have to change the value of that particular number, and you can find out those things. So if we are looking into an inverter which looks like this one, when we have started studying this, we made the simple model, which was the resistive model. There was no capacitance. However, we have considered the load capacitance in your circuit, and this is RP. So when you are moving from high to low, we assume that it's RP times CL times 0.69. That will be the propagation delay. Whereas in the case of high to low to high, it's going to be equal to low to high, high to low. It's going to be equal to Rn times CL times 0.69. But this is not the complete picture which we have discussed last time, and even Srinivas has asked the question that how much capacitance will be there. So look, the capacitance here right now, we have assumed that it's only CL, but if you assume that it's a high frequency model, where there are capacitance will play the role. So if you look at PMOS, now I'm not drawing the cross-sectional area of an inverter. So in that case, you will observe that there will be overlap capacitance whose name is gate to drain, and another one is gate to source, CGS, and another one will be C drain to body. It's yeah. So these are the things are going on, and input is input. When you are interested in finding out the propagation delay, which is going from low to high, you have to follow these capacitances. At that time, I assume that there are no capacitance, by the way, offered by NMOS, because it's in cutoff. So there is nothing is going to be contributed by NMOS at all. So if we are deriving the propagation delay with that assumption, I know that the resistance in this particular transistor, first of all, we need to find out that. So that resistance is going to be the on resistance of this transistor, with the fact that this transistor is in triode mode of operation or the linear, because that is the expected thing from this PMOS, because I'm interested in a design where complete VDD will be transferred over here without making any mistake. So our P is the resistance which will be in the equation of triode region, how to make VDS. So del ID by del VDS is going to give you the resistance, and ID triode is nothing but Kn times VGS minus VTH times VDS minus VDS square by 2. When I'm writing this equation, I am not assuming that there is a channel and modulation. However, if you are interested, I suggest to add 1 plus lambda VDS, where lambda is a constant and it's a ratio of channel length L to the lateral diffused length of delta L. So L by delta L is going to give you the lambda. So it's up to you. If you want, you can use it, because this is the real term which is going to be happen in your simulation and everywhere. But if you want to make the system a very easier one, you can drop this. There is no problem. Just you have to write the assumption on top. But if you have been asked specifically that you have to include the channel length, then you have to add. There is no escape for that, right? And similarly, body effect is also there. Then there's a few more equation will be changed, but that is the extreme one. It's not going to happen. So you have to take the derivative of this one with respect to VDS. You will find out what you want. So you will see that it's a simple equation, and this is going to be you can derive it, and it's given in every book. So I'm not deriving it. It's very easy. Okay? All the books are keeping that. Note that this is a constant. VDS is already known to us, and VDS square by 2 is also known to us. So just take a derivative and you will get the answer. It's very simple answer, you will get it. And that is what you need to feed over here in RP. But the next question is the load capacitance times 0.69. But this is the case when there is no high frequency model has been considered. However, in our case, we are considering the high frequency. So in that case, notably, I forgot to keep here one more capacitance, which is from gate to body. So there is one more gate to body known as CGB, which is actually COX capacitance, by the way. Okay. So CL plus you are going to have CDB plus CGD. Rest of the capacitances are not coming to picture right now. So this will be the total capacitance, and propagation delay going from low to high will be that much. Notably, when we are doing this analysis, I'm assuming that you are well aware that VDD is not equal to VDD, but it's ground, and input is also not moving, because we assume that it's either VDD or ground, so it's also ground. And for ease of calculation, when you are doing this, rest of the capacitance will be vanished, because between input and output, it's a short circuit, because this capacitance, both sides are same plates, they are not dissimilar. And note that we are doing this because of the reason that they are the AC ground. So these are the AC ground. Okay. So in that case, you can have all these capacitances in picture, and this will be the low to high. Similarly, you can find out high to low capacitance, which is going to be equal to Rn times. So let's keep the transistor and keep all the capacitance. So CGS will be removed. Both sides are ground. Notably, this ground is shown over here is DC ground, but we are talking about the high frequency model where it's ground. Okay, so in that case, you are going to see different capacitance. Those capacitance all are in shunt, so all will be added in phase. So CL plus CGD. Let's make this one as P and this one as P so that life is easier. So CGD plus CDB and times 0.69. So this number is depending on the fact that we want to see the propagation delay exactly at 50%. So that's why these numbers are coming. Uh, Other than that, we need to understand few more things in terms of capacitance, which says that so there are two kinds of capacitance you are going to see. So these are the junction capacitance. These two are overlap capacitance. This is gate to body capacitance. Generally, that capacitance is COX, by the way. Generally, so this gate to body, but let's call this one separately because this is oxide capacitance, and that's equal to Tox by epsilon x. But similarly, like in many books, you will not see this one, but you will see something like this. So there is one more notation where you have prime on top of that. So COX prime, CGB prime, C, all these primed, both have some different units. The unit of this capacitance is equal to the, the capacitance, which will have the unit of farad. However, in this one, it's a capacitance per unit area. So this capacitance is actually divided by the capacitance is given in left side with respect to the unit area. So if the minimum area given for the technology is 120 nanometer length and 220 nanometer of width, then you have to divide with that one with the unit area, right? So that's how they have to be calculated. And because of that, if you look at the COX and if you look at the COX prime, the unit of this one is farad with respect to area, so it has to be some area, generally centimeter square, micrometer square, right? Depending on what unit area you are taking, right? So it's micrometer square, centimeter square, or nanometer square, whatever you are following, right? But it's a per unit area. So by looking at this, if I want to find out the COX, actually it's area times COX prime. Notably, the area is W times L times COX. So this COX is nothing but W times L times COX prime. So do not get confused with that one. And whenever you want to have the capacitance, you have to multiply with the area. Otherwise, you will get the wrong answer. Or it will be different capacitance whose unit is farad per area. Okay. So there are some you can say that if you go to the website of UC Berkeley, the same group where Professor Rabe is also working, and he has written the book, and the book which I am following for the course. So there is some wireless group is there. So in that group, there is one more group very famously working, and it's known as BC. It's known as Berkeley simulation model. Simulation models. This is very important at this point to understand that these BC models are very popular for the fact that when you are saying that I am simulating this, When you are saying that I'm simulating this, actually you are not simulating this as a symbol. What do you think? What will be inside this schematic? Inside this schematic, if you go inside, it's not something like this. It's unfortunate that it's not like this in schematic. It's a layout, by the way. This is layout, which is working on parasitic things and other things. But for schematic, you are going to have its IO equations. If you have studied somewhere like in control theory or other courses where everything is defined by input, output, sometimes few more things also which are disturbing that, and you are writing output in terms of those parameters and defining that. It's also known as transfer characteristic or the transfer equations or the transfer functions which you are using. So if you're going inside this, there are mathematical equations are there. Right? So how does they look like? This equation is already known to us. So this equation should have been written over here. And how did they find out? This is from the experiment they found out. So if you go back and the history of maybe Shockley and all people who have started the BJT and thereafter MOSFET and other things, they have done the experiment, and through the experiment they draw the characteristic, and through the characteristic they found out the equation for different region. This is what we used to do when we were studying physics or chemistry or biology or other things in school time. So you must have experienced that you used to find out that which equation is following from that particular experiment. So that is what they used to do. But here the question is whether this equation works now also. When I'm saying now, means we are in the deep submicron technology. Maybe we have started with the micrometer channel length. So earlier time, maybe almost like in 70s, when like one of the processor came into picture. So that processor was in micrometer, right? And they were making the calculator. I found out like one of the student has made this post on LinkedIn. So I have seen it, and yeah, I also learned that they try to make the calculator using that processor. So it was some old with the some series of 400 something was there. So Intel processor before 8085, 5180, 86 and all. So as you are going down, so in micrometer, this equation what we have written might be valid, and it was not giving us any problem. It was following this. You might have seen that this equation is following when you are doing the experiment in the laboratory with the discrete component where the transistor size is in micrometer or much higher than the micrometer. It was working there. But as you are going down with the Moore's law, right now we are as near as 5 nanometer, or we are working in 5 nanometer technology node, where just imagine that what I have drawn here is actually 5 nanometer channel length. So will this equation will work? It won't work. Look, if you are using it directly, it won't work. So, and we also understand that we want to see that my entire circuit should work for different process corners, voltage corners, and the temperature. So as per our knowledge that even Ohm's law is only working at the room temperature. However, if you are going at different place, like if you are applying the KCL, KVL, that will be fine in maybe space technology or other places. However, if you are using Ohm's law, in that one, it will not be same because temperature might not be same, so voltage might not be same. So the whole thing is all this equation which is characterizing our NMOS or PMOS, all this needs to be actually find out. So sometimes these equations are as big as, you know, 1 page, 2 page, 3 page. So you need to understand that, and that's why there is one specific uh, branch of study, or you can say that the engineers, process engineers, or the compact model engineer who are expert of device physics, and that is how we have one course for MTech VLSI. It's known as microelectronic devices and compact model. So which tell us that, or for our BTech student, it's a device electronic for integrated circuits, where you are studying the compact models and you have following approaches to understand that. So those approaches are saying that, look, the intelligent engineer maybe say that, look, let's uh, let's look at the characteristic ID versus VDS. Look at the characteristic, break that in 3 different regions: cutoff, triode, and saturation. Write down the separate equations, and these equations are being written by, there is something called surface potential. So you know that what is the surface potential. Generally, this surface potential is written by psi s, by the way. Okay, with the Greek letter psi and with the subscript s. So this is surface potential. So to understand this, you definitely need to understand the band bending diagram also. Some people are also calling as BTB diagrams. Okay. If you are not studied, don't worry. Or if you don't understand band bending diagram right now, it's okay. If you understand that, then also okay. So on the basis of surface potential, you are making 3 equations, and those 3 equations can be written and can be checked with the original device which is made in 5 nanometer. So in the company, those who are the compact model engineer or the process engineer, what they are doing, they are fabricating the device in 5 nanometer. They are looking at the IV characteristic, and they are checking all the parameters with respect to what they have derived mathematically, and some of the fitting parameters needs to be added. Look, it's not only this one, but it needs fitting parameters also. Some alpha, beta, something will be there which is going to fit this parameter, and they will do the experiment almost on like something like 1 lakh devices or something like that, or more than that, and those will be useful to characterize these equations. And that's why, look, right now, if compact model engineer is working on 1 nanometer, then the design engineer is working on 5 nanometer, because these models has to be ready for the design engineer. Otherwise, we can't work, right? So this is what happening. So this was one way to do that, but there is another way also to make the compact model, which says that do not go with the surface model, because this is not the fundamental way to derive all these things. The fundamental way says that write down the charge shift models using maybe Schrodinger's, and use the boundary condition, Poisson equation, all this, like do the rigorous physics and have following equations: QG, QD, QS, QB. Take the derivative of all of them with respect to time, you will have the current equation. And through that, you can find out the characteristic ID versus VDS. So there are 2 different ways to do that. So these things are happening, and what is generally being done? as per my knowledge, maybe like some things might be changed, but there are two different tools are there, Spectre and Aldo. Spectre is the one which is belongs to Cadence, and Aldo is the one which is belongs to Mentor Graphics. Both are competitor to each other, but have different models. So when you are running the simulation, when you are saying that you are running the BSIM Spectre simulation, you are using surface potential approach, whereas if you are using Aldo, you are using the charge sheet model equation. So internally, this is what happening. So these models are written there, and those models are being used to find out the values of all these things. But now let's understand one more thing, that generally the symbol of PMOS looks like this one. And as I told you that drain and source are interchangeable, it's okay, fine. You can interchange it even if this is, let's say, source is connected to some other place like this, and drain is connected to VDD. Because we have connected drain this terminal to VDD, which is higher than this terminal, so automatically this becomes source and this becomes drain. But I suggest do not do this one. Do not do this one. Although they are interchangeable, but it's offensive work to do this one. You have to connect source over here and drain over here. Not only because source is written over here, but in the model, the CGS, CGD, or all the capacitance associated with source, which is written in the model file, means this one, it's associated with this particular node only. So if you replace this like this, you can replace this, your circuit will work, everything is fine, but you cannot find out that the problem. So automatically this will be considered as source and this will be drain. However, when you are running the high frequency model, that might be the case that you are seeing some difference if these two capacitances are not equal. Okay, because this might be happen. Okay, so because of the model parameter, we don't do that. So this is one advice to you people. So please follow the notation as required. Okay. Next thing is, so if you are following these PSIM simulations, wherever you are seeing this, they are having some labels. Label means they updated themselves, and they have written the higher models, and using those models, they are writing the different ID and other equations. When you are going to run the simulation, you are going to see the model parameters, something like model parameters. Maybe I'll talk about this maybe when we are going to see the real model parameters. You will not be understanding right now. So I'm saying BSIM level 8, 10, 9, whatever it is. So it's, complexity is increasing with respect to this level. This is one thing. And because of this simulation model, as I told you, Cox is equal to W times L times Tox by epsilon Xox by Tox. So using this model, which is given also in the Rabe book, you need to see maybe somewhere preface or some particular like at the starting, those capacitances are given, where they are recommending that in different region, they also call it switch, or they also call it resistance, or we also call it linear. So all these different region, you are going to have the different value of the oxide capacitance or contribution of the. So we don't care about the cutoff; they will be as good as 0. But if you are in saturation or triode, these numbers will change. So what these numbers are saying, so these overlap capacitance CGD and CGS are actually half of what we have this W by L times whatever the CGD, CGS you are seeing, CGD prime or CGS. This is half because we assume that both sides there are equal overlap. Because of equal overlap, it's half that has been approximated. By the way, these numbers are approximated and given by some of the model developing guys. So I'm following that. Otherwise, you can take COX if you want to take it. Do not take some number associated with that. So if you are interested in saturation mode of operation, the COX does not stay as COX, but it's 2/3 of W by L times COX, and this becomes half W times L times CGD prime, and so on. So you can see these numbers. These numbers are changing, and these numbers are different depending on the technology also. So these are just for some reference given in many books. You can refer if you want. It's also given in Rabe. It's also given in Kang. It's also given in Weste and Harris. There are two guys. This Weste is different and Harris is different. Harris is from David Harris is from Stanford. He is from UC Berkeley. So you can follow that. So with those equations, you can approximate the exact propagation delay, because sometimes it becomes multiplied by 2/3, or sometimes it becomes half. So those numbers will be useful. These are as good as it's a fitting parameter kind of thing, and from there it's actually following in most of the levels. That's why they have been given over here. Okay, so I believe you understand this capacitance and other things, and you also understand the propagation delay is equal to 0.69 times the path resistance times the capacitance associated at the node wherever you want to take. If you want to take it at output, it will be CL plus some of the capacitances, or if it is not CL, CL is not given, and if it is self-loaded, then you have to keep all the capacitance which are coming into shunt to each other. That has to be kept over here. If you look at the calculation wise, although we achieved the answer, but still if you are interested in finding out the equation through the like propagation time which is required in to go from logic 1 to logic 0 or logic 0 to logic 1, it's equal to integration from V1 to V2 logic. These numbers are coming from the fact that you are going from logic 0 to 1 or 1 to 0, so you can change it accordingly, and CL divided by I is going to give you the time to propagate. So now if you are interested at 50%, you have to keep this value at ln 2 with R equivalent times CL, so it will be 0.69 times CL, and you can have similarly like propagation delay for high to low and propagation delay from low to high. If you look at all this calculation, there are two kinds of propagation delay we found out, but generally we are saying that this inverter has a propagation delay of something like 1 microsecond or 1 nanosecond or 1 picosecond, whatever it is. So that number is depending on the average value of these two. So when you are saying that it's propagation delay only, it's divided by 2, it's average value, and if it is just TPHL or TPLH, you know what are these numbers are. Right? Now, if you want to reduce the propagation delay, because sometimes you will be asked to design your inverter with one of the specification as propagation delay. So if you want to reduce it, what you can do? So you have only very limited things in digital design. You can see that W by L of NMOS, W by L of PMOS, this is VDD, this is ground, this is input, and this is output. So my whole agenda is I want to reduce this propagation delay, which is actually the proportional to path resistance times the capacitance associated with the node. So I want to decrease this resistance and decrease this capacitance. So the first thing is you can reduce the load capacitance if there is any. Okay. If it is not there, then you have to tune this WL of this one. But the first choice with the load capacitance, let's reduce it. If you reduce it, then like you will get better propagation delay. So this is what written over here. Second thing which you can do is increase the W by L. Look at this. Increasing W by L will reduce the resistance. So if you look at this resistance, on resistance, which is equal to del ID by del VDS, when this transistor is in triode region, and this equation is nothing but Kn times VGS minus VDH times VDS minus VDS square by 2. If you derive it, this becomes simply, this is, all these are constant. So, right. So you have to take the derivative of that and you will get the answer. So you will see that it's only and only, it's only, you can say that W by L. So it's coming in proportion to Kn when you are taking del ID by del VDS. So in that case, it's only W by L, which is actually giving you, okay, by the way, this is 1 by del ID by, sorry, that was a mistake from my side. So when you are having this, it's in proportion of W by L. So this goes in inversely proportional to W by L. So if you want to reduce resistance, you have to increase W, or you can, again, you can reduce L, right? So it's L by W. So generally we don't touch L because channel length, we are going to keep it minimum channel length, right? And as you are increasing the W, your resistance is decreasing, and that is what we wanted, to have lower resistance. But sometimes you are increasing and lots of things you are doing, but the problem here occurring is as you are increasing the W by L, at the same time you are increasing the node capacitance, because if you understand, the Cox becomes, C is W times L times whatever C is there. If it is Ox prime, CGD, W times L times CGD prime, and so on. So everything is multiplied with area. You are not touching L, I understand, but you are touching width. If you are increasing width, you are increasing capacitance. So if this, as per this equation, if load capacitance plus some parasitic capacitances are there, so if these parasitic capacitances are becoming comparable to CL, then your propagation delay will be affected. If you are increasing like W, you are decreasing resistance, no problem. But if you are increasing these parasitics such that it's comparable to load capacitance, then your overall propagation delay will be not reducing, but it may become worse. So it is a trade-off. You need to find out that point. Some of the things you can find out through the model, some of the things you can find out from the intuition, and some of the things you can make the intuition from simulations. Okay. And the third one is like increasing VDD so that you have higher voltage, so that there is, in physics, it's a term called hot electron effects. Because of hot electrons, you will have the faster electron movement, and because of that you might have a better propagation delay. So it will be reduced. So that can be done, but it is suggested that you should go just plus or minus 10% here and there. If you are going beyond that, it might create oxide breakdown, means your transistor can be damaged. We don't want to do that. And there are some reliability concerns, means it's like, as we are saying, it can be damaged, so we have to make sure that it should not be damaged. Right? So I think that's all for here today.